Good morning. Here I will give you two talks. The first talk is preprocessing in PS space in preparation for onshore seismic processing, removing ground roll and ghosts without damaging the reflection data. And in the next one, I will show you preprocessing in displacement space. Okay. Both talks are sitting on the top part of this tree, and say we do set of preprocessing to obtain the reflection data without the ghosts. So why is this important? All the lower branches are the reasons, because they all depend on this, especially for the free surface multiple removal and the internal multiple removal. They immediately depend on this. And actually not only for our own interest, but for the general interest of seismic processing, we also need to make this kind of pre-processing happen. So looking at this circle, we can see green serum has two jobs to be finished. The first is it has to separate the reference wave from the reflection data. And the second job is the green serum need to remove the ghost of your reflection data. And in this talk, I'd like to show you how do we apply the elastic green serum to meet this kind of prerequisite. Okay, before we look at the algorithm, let me show you how what's the data data requirement of this method. And here we look at 2D data, and it can be extended to the 3D world. Okay, here we assume overall people measure the displacement, and you have your source like the vapor side has x direction and the vertical direction force. And also for the receiver like the gel phone, it measures the displacement in x direction and the z direction. And besides this, there are some seismic processing require the data in the form of PS space, say P wave and S wave. For example, the medicine and Wagner just provide the multiple removal algorithm for the elastic data, and their work just starts from the data in PS space. So based on this kind of interest, we here just provide an algorithm to separate these other reference wave and ghost in data in PS space. And okay, so the first thing here is we need to transform the data from displacement space to PS space. I will comment at the end about this transform method. Okay, now in this new basis, you can see the original data in the original source with fx and fz is decomposed to be ps and s source. So for p source, it only has its contribution in the radial directions. So assume a homogeneous area in the vicinity of the source, it will send out the p wave. And for a p wave, now assume this is your plane waves. This is your plane wave's propagation direction, and the p wave will have its particles vibration direction parallel to this propagation direction. And for the S wave, it only has its contribution on the tangential directions. And again, assume a homogeneous area in the vicinity of your source, it will send the S wave out. So for S wave, it has its vibration direction perpendicular to the wave propagation direction. And now if you are in the heterogeneous world, now even for a single source component, it will give you both P wave and S wave. Here we use phi P to represent the P wave at your receiver side, and we use phi S to represent the S wave at the receiver side. Okay, now our algorithm requires the multi-component elastic data, and we have our data in these two spaces. Okay, we just provide the wave separation algorithm for these two data sets, and you can pick an appropriate one for your own interest. And the bottom line here is no matter your data in PS or in displacement, the green serum wave separation idea, which was given by Dr. Wagner in his tutorial, is always the same. And specifically, this elastic case is just a grown-up version of the marine case. And in this talk, I will show you how what's the algorithm and how it performs for data in PS space. And in next talk, I will show you the algorithm if you have your data in displacement space. Okay, this is the outline of this talk. First, I will show you the reference and the scatter wave separation, the reference and the reflection and the reflection wave separation. And the second, I will do the next step to the ghost of your reflection data. And after that, I will show you some comment and discussion about this method. The end is the summary. Okay, let's look at the first part. And before we study into the elastic world, I'd like to use a very simple example to repeat what Dr. Wegland said in his tutorial about the Green theorem wave separation. And now imagine you have a homogeneous world and you have two sources. So the actual wave field will be what these two sources produce in this homogeneous background, P1 plus P2. Okay, now Green theorem tells us that just do the surface integral along this closed surface and evaluate inside the volume. Then you can get the contribution due to the S1, due to the source S1. Say S1 acting on this reference medium give you the wave field P1, and it will be identified after you do this integral. And this is the integral formula P grad G minus G grad P. G0 is the Green's function in this reference medium. And later we will just extend this Green theorem idea to the elastic world. Okay, now let's use this line data example to step into the elastic world. And here you can see this is your reflection data, and this is the ground rule. It's very strong, and we know this is interface wave generating at the air-earth boundary. And we are interested in identify and remove these waves. And we are aware that the ground rule removal is a non-trivial problem. People are looking for better approach to remove these events and preserve the reflection data. And the linear filtering method like FK could be chosen, but those kind of methods may damage your reflection. So here we provide the elastic Green theorem wave separation method to separate these events and return the energy of your reflection data. And we fully aware that the major issue of wave separation for land for both on-surface and buried sources and receivers is the near-surface complexity, and it's time-varying and unknown. We are committed to address these issues. Well, right now, let's just assume the near surface is homogeneously elastic and known, and our wave separation activity in this part is within this assumption. And I will comment at the end about the other activities and plans within our group to address the other issues for more realistic situation. Okay, now within this assumption, we can have our experiment model to be air and then some homogeneous near surface, and then suddenly to be non-homogeneous marked by this dark brown. And here we assume the Earth right below the free surface is known. And in this PS space, we have a source in the air. It can only send the P wave out, so it's a P source. And it can be infinitely close to the free surface, like the Weber size, which is exactly sitting on the free surface. And at the receiver side, it's sitting on the measurement surface, and we use these triangles to represent the receivers, and it can measure both P wave and S wave. Okay, now we choose the reference medium to be half space air over half space elastic. And we assume that this reference medium agrees with the actual Earth on and above the measurement surface. Then we will have these two sources. The first source is above the measurement surface, and it will give you, acting on the reference medium, it will give you the reference wave. And on the other side, we will have the Earth's heterogeneity, and acting on the reference medium, it will give you the scatter wave of the reflection data. Okay, so for the reference wave, it will have the direct transmission or direct wave, and it also has this kind of surface wave. Well, these events are exactly what we like to separate at the beginning of this part. So as long as we can effectively separate the contribution from S1 and the contribution from S2, we can separate these events from the reflection data. Okay, remember the S1 and the S2 in that homogeneous background, and here it's grown up in the onshore experiment to be like this. And following that idea, we choose the Green theorem to finish the job. Okay, now we put a closed surface, and its upper boundary is the measurement surface, and we put our evaluation point inside the volume or below the measurement surface. Then Green theorem tells you that do the surface integral along the measurement surface, and it will give you the contribution from the source that is outside the volume. For this case, S1 is outside the volume. Now, acting on the reference medium, it will give you the reflection. It will give you the reference wave, and it can be separated after the integral. And this is the integral formula for this 2D world. And remember that P grad G minus G grad P story, it grows up in the elastic world to be like this. And the same formula, the same general form, but more complex in detail. And let's look at this formula here. Phi, as we saw before, is the total wave contains both P wave and S wave. And grad phi is gradient, and G0 is the Green's function in this homogeneous reference medium, and the grad G is its gradient. Okay, so now as long as we have all these four terms, we just put it into this integral formula, we can have our reference wave separated. Here we use phi 0 to represent the separated reference wave. It also contains both P wave and S wave at the receiver side. And I'd like to mention, remind you that when we do this integral and identify the reference wave, there's no need about there's no information about the source outside the volume. So this integral formula doesn't need to know any information about the source wavelet, and it doesn't need to know any radiation pattern of your source. And the other thing here is if we look at this integral, it's just integral along the receiver point, but not along the source side. It means that this works on one experiment at each time. So given a short, it can be separated on its own, and less data requirement. Okay, similarly, if you put a closed surface like this, and at this time, its lower boundary is the measurement surface. Again, if you put your evaluation point inside the volume, at this time above the measurement surface, then you can get your reflection data separated. And I'd like to mention here, like Dr. Wegler mentioned in his tutorial, when we do this kind of integral, there is no limitation about the measurement surface. It can be flat, inclined, or even undulate. And this integral formula can handle all these situations. Okay, next, let me use one model to show you how this algorithm performs to separate the reference wave and the reflection data. And for this test, I just located the output point on the measurement surface by doing the formula in Fourier domain. And this is our model here. Here we have air and a two-layered elastic earth. And we put the source on the free surface, and it's a P source. And we put the measurement surface 5 meters below the free surface, and it can have both P wave and S wave. So now assume we can also have its gradient, and we have the Green's function and its gradient. We just put all these terms to that wave separation formula. We can get our reference wave, all scatter wave separated. Okay. So here I just show you the P wave component, and this is the input data of the total wave, the P wave component. Here we can see this is the relay wave, and this is the direct wave. These are the reflection data. Clear to see the relay wave just dominates the energy here. And now first if we put the output point on the measurement surface, but arrange it to be part of the lower volume, we can have the reference wave separated. Okay, now if we compare this separated reference wave with the reference wave of your data, you can see both the amplitude and the time are matching very well. And I'd like to remind you, we get this reference wave by applying the elastic gradient theorem using both phi and its gradient on the measurement surface. And similarly, if you put your output point on the measurement surface, but to be part of the upper volume, you can get your reflection data separated. Okay, now from this example, we can see the gradient theorem has its capability to effectively separate the reference wave and the reflection data. And next, I'd like to go to next step to show you how to degauss the reflection data. You know, for the reflection data, besides the upgoing wave, it also contains the downgoing reflection, or we can call this the ghost. And what we do now is trying to separate this downgoing wave from the upgoing reflection. And again, this is our experiment, the sixth experiment, but there is no reference wave now. And at this time, we choose the reference medium to be a homogeneous elastic wall. And this reference medium has its property agrees with the actual Earth along the measurement surface. Then now we can have these two sources. The first source is the air perturbation, and it will give you the ghost. And the second source is the Earth's heterogeneity. It will give you the upgoing reflection. And again, here we use the gradient theorem, put such closed surface, and put the evaluation point above the measurement surface. We can effectively get the contribution from S2 or get the upgoing reflection data after applying those integral formula shown here. Okay, next I use the same model to show you how do we remove the downgoing wave from the upgoing wave. And this is the same experiment. Again, I just show you the P wave component. And this is your reflection data. It contains both the upgoing wave and the downgoing wave. After we apply the gradient theorem, we can obtain this upgoing reflection data. And this upgoing reflection data is obtained by using the gradient theorem. Okay, to evaluate this result, it just create the ghosted P component data. Means that we just I give the model to generate the data. Also, I can generate the data only contains the P component upgoing wave. So we can treat this data as an accurate result. So now we compare the accurate result with the calculated result. This is the calculated result, and this is the accurate result. It means that it's really hard to see any difference. So until now, we can see the gradient theorem also have its capability to remove the ghost from your reflection data. Okay, now I'd like to give some discussion and comment about this method. So first is the data requirement. Let's back to this integral formula. You can see in order to apply this integral formula, we need to have phi and grad phi. Say to separate the reference wave from the reflection data, you need the total wave field and its normal derivative. And for the second step, if you like to remove the ghost from your reflection data, you need to have the reflection data or scatter wave and its normal derivative. And the third thing here is if you have the source signature, you can arrange to replace the requirement of the normal derivative. And as I mentioned at the beginning, we do this algorithm in PS space. So here I'd like to show you how do we transform the data from displacement space to PS space. Okay, so in order to obtain the data in P and S, we need to apply the divergence and the curl on the displacement. say in order to do this, for both ux and uz, we need their derivatives along the x direction and the z direction. And then the second is identifying the near surface. To do this experiment, I just assume that we have the homogeneous near surface and its property is known. And I also mentioned we fully aware that the major issue of the wave separation is the complicated near surface. And there is some ideas and plans within our group to address this issue. So the first is my colleague Lin just used some invariants to back out the near surface properties. And here is one piece of Lin's work. And here we assume the reference wave is a convolution of wavelet and the Fourier function in the reference media. So as long as we can separate the reference wave, we can estimate the wavelet by using the reference wave. And based on Lin's work, we found that if your reference wave has the accurate velocity here for 1500 meters per second, you will have your estimated wavelet invariant along different offsets. Otherwise, if your background velocity is not accurate, you will have this wavelet. Say it will have a different shape along different offset. So based on this result, we can just to use this invariance to back out the near surface properties. And here he just consider a homogeneous reference media. And I like to extend this idea to back out the near surface properties with lateral variance. And the second way we are approaching now is Dr. Wegner is developing the wave separation for buried sources and receivers without knowing any information above, below, or at the environment surface. Okay, the end I like to drop the summary. Here we look at the data in PI space, and the elastic Green theorem shows its capability to effectively remove the reference wave, especially the ground rod, from the reflection data. And it also has shown its effectiveness to remove the ghost from the outgoing reflection. And finally, we can obtain the outgoing reflection data for the next free surface multiple removal and internal multiple removal. So everything here we do is try to provide the effective prerequisites for the following multiple elimination for land. Okay. At the end, I'd like to thank our sponsor for the support and the encouragement. And this is the first talk. Thanks for listening.